In this series of videos, we've been looking at within subjects designs, and in a recent video, I did descriptive analysis with the sprint data, which used a repeated measures design. What I'm going to do now is continue with the analysis, but this time getting into inference. Now, to proceed with inference, we need to switch to the long format. Probably the easiest way for me to introduce the long format is to show it to you. Let me actually go ahead and look at the wide data again. That's the wide format. Now let me compare that to the long format that I've created, and then I'll come back and look at my commands here for the long format. But I've actually created long format in a data file that I've called long, and let's go ahead and contrast this with the wide. So here is the long format. Notice that what we've done is we've included the ID numbers and we've included the trial number. So for every row, I have just one observation. You remember in the previous video, I talked about how we could take a multivariate approach or a univariate approach. This course always uses the univariate approach for all our analysis, which means we have a single response measure. That is why we have to switch to the long format. If I was going to do this using a multivariate approach, I would leave the data right like that. But notice that for every individual now, we would have 6 observations, 6 response measures. That's multivariate. The univariate approach, meaning univariate on the response measure, not meaning that you're only looking at a single variable. We're not. We're looking at other variables as well. But we are leaving the response measure to be univariate, the single variable. So here it is. Time is our response measure. And now I have 42 values of time, 42 observations. The observations, however, consist of coming from a person at a particular trial. So that's what we have for these two values here. We have a factor. One factor indicates which person it is. Notice that's not a quantity. Going from 1 to 2 to 3 does not mean you're getting more and more individuals or more of an individual. And similarly with trials, going from 1 to 2 to 3 to 4 to 5 to 6 doesn't mean you're increasing a number of trials. It's the trial number. So these are just numerals, not numbers. And we have to treat them as categorical data. That is, they are categorical data. So we're going to have to set these up as factors. So we've taken what's here in the wide condition. We've taken the individual numbers that you see here as the row values, and we've taken the trial numbers, as you see as the column values, and we've put them into 2 separate columns, one for the person, one for the trial, with a univariate time response variable for all 42 observations. So here I've loaded in the long format that was already created this way, but now I'm indicating that my ID is a factor and that my trial number is also a factor, leaving, of course, time quantitative as it is. Now it's time to set up the model. And we're doing something here that you've not seen in previous videos in this course. We're specifying the error term in the model. The reason that we haven't had to specify that before is because in each of the other models that we've encountered, when we put in the factors of interest, or if we're doing quantitative explanatory variables, we put in those quantitative explanatory variables of interest, everything that's left over was our residual. Everything not in the model was our residual. But it's different this time because we're dealing with within subjects factors. So I hope you remember, and if you don't, you may want to go back and look at it. When I was first introducing within subjects factors and telling you why we can actually get more power with these factors, I talked about the fact that you actually have two sources of variation, and one of those can be removed. The two sources of variation are the source of variation between participants. Okay, that's the between participant source of variation. And then there's the variation across the factor of interest, which is our time trials within each individual. That is, each individual has, in this example, 6 trials, and there's variation that can occur across those trials that is not explained by the mean of the trial. The means of the trials are estimating our main effective interest. And that's shown right here in the model. Just as we always have in all our models, we put in the effective interest. We're interested in trial. But what it doesn't explain is why individuals within individuals vary from the mean across the different trials. That's not part of this effect. This effect here is focusing on the trial itself. That is, we're using the mean and the changes in the mean from one trial to another to be the primary effect of interest. But people don't all stick at that same mean, and they don't stick at their own mean. They vary across individual trials. So there's two types of variation. Variation between individuals, which we want to remove, and variation within individuals. Now, when you look at this error term, the way that R provides the error term and the way we think of the error term is that when you have that slash there that I have right there in the middle, it's whatever comes after the slash is what we call nested within what comes before it. So what I'm doing here is I'm looking at how does trial vary nested within person, and how trial varies nested within person is a source of variation. That is the variation that we're interested in using for the error, what is not explained by the mean. Okay, the fact that people are not all at the same trial mean from time to time to time means that people vary within how they respond to the time of the trial, or to the trial number, the trial attempt, 1 through 6 in this particular example. So we want to not include the between subjects variation because we're focusing on trial, and trial is being conducted by each individual. Each individual participates at every trial. So we want to focus on why those individuals vary across the trial, not why those people vary from one another. What would happen if I did not put that error term in there? If I did not put that error term in there, then what would happen is that we would end up with the between subjects variation and the within subjects variation all being combined together. I don't want that. That would reduce my power because remember, error is going to be in the denominator of our F statistic, the mean square error. I don't want that between in there because I'm only focusing not on between subjects, but I'm focusing on what happens within subjects with the trial. And that's what gives us the power of within subjects design, is removing that between subject variation that we're not interested in. So this is saying, please only use the within subject error. This is saying, here's the main effective interest. And this is how then we're looking at our response variable time. So this model is looking at the response variable time as a function of what trial is the individual in and why might that individual vary from the mean for that particular trial. So that's what we want to focus on here. So that's where this comes from. This then will give us, I'm going to store the results using the AOV, which you know stands for analysis of variance. I'm using the AOV with this particular model, and I'm going to store those results because I'm going to use that stored result in order to check our conditions for valid inference. So let me go ahead and run this. Now we need to look at our diagnostics plot, and we need two of these. We need one to look at the normality condition for valid inference, and one to look at the sphericity condition. Remember, the third condition is independence of our observations, and that's a design characteristic, not a statistical one. Unfortunately, looking at these plots are not as straightforward when we use a within subjects model. First, we need to get the residuals, and we do that by using what is called a projection matrix, and that goes beyond the mathematics. That's a matrix issue, and I leave matrix manipulations for my multivariate courses. This goes beyond what we're doing in this class with univariate. So it's good that what we're doing is using R functions. And I'm deviating from what I usually like to do, which is to make sure you understand every function that you're using in R. I'm deviating from that by saying, okay, what you're doing is you're creating a projection, and you're projecting those explanatory variables onto the response in order to separate out the effects from the residuals, and that will give you one component that you can then extract from the more results, which is going to be the residuals. And so I probably just said a bunch of stuff that you say, I don't understand and it doesn't make sense, and I'm admitting it does not. So I'm simply giving you the commands for doing this and saying, if you want to learn more, look up projection matrices. You can look that up on the web. And using R, you can see how the projection function, PROJ, how it produces results from which you can extract the residuals. And so that's what we're doing here. Why do we have to do it this way? Well, there's another way we could do it, but this is actually the way that's more consistent with our model. The other way would probably actually be easier for you to understand, but it would not be consistent with the model. I'll mention it a little bit later on. All right, so let's go ahead and run this. And now this part you're familiar with from earlier videos in which we get the QQ norm and put a line through that in order to get a QQ plot. And what we're hoping is that our theoretical quantiles and our sample quantiles match up fairly well. And in fact, here it matches up beautifully well. This is a very nice illustration of having close to normal distribution. So I have a close to normal distribution, plus I have 42 observations. I'm in good shape here. All right, if this was off, if we were seeing something happening in terms of, say, skewness or over-dispersion of our residuals, we might have a reason to be concerned that our inferences that we're making might be substantially off in terms of our confidence levels from what we're using for our calculations for our confidence intervals. But here I'm good. All right, now we need to check sphericity. What sphericity is the easiest way to put it. There's a lot of complicated definitions, but I like this one the best. This is the easiest way to put it. Sphericity is homogeneity of variance among all pairs of differences. So I'm literally, there's other ways to do this, but I do it this way because I think it's the way that makes most sense when you're first learning about it. I am literally creating all pairs of differences. What do I mean by pairs of differences? Well, look here. I'm taking all the differences between trial 1 and 2. So remember, we had 7 individuals in our data set. So let's go ahead and put those up. In fact, I'm going to show it in the wide format because it'll be easier to see where those differences are coming from. So here are 7 individuals at trial 1, 7 at trial 2. What I'm taking here is I'm subtracting trial 2 from trial 1. So if you look up here, this one, I'm subtracting this trial 2 from this trial 1, and I'm doing that for all 7 people in order to get 7 differences. And I'm subtracting 3 from 1, 4 from 1, and then I do 3 from 2, 4 from all the way down until I finally do trial 6 from trial 5. That gives me 15 different pairs of differences, all possible pairs of differences that we have here. Remember that we had 6 different trials that we saw right here, 6 different trials. If you want to know the shortcut for how to calculate pairs of differences, it's the number of the measures we had, 6 minus 1 is 5. Multiply that together. 6 times 5 is 30. Divide by 2, that gives you 15. And that's what we have here is 15 pairs of differences. Now what I'm doing down here is I'm putting all those differences in a vector. That part might be easy enough to understand. It should be that I'm just putting these 15 differences in a vector. But this one here, you might say, what am I doing there? Well, what I'm doing in this particular line is I'm just creating a coding variable for each of the 7 participants. That means each equals 7, so that I have 1 through 15 for each of the 7. So I have 15 differences, but I also have those differences for each of the 7 individuals. And so that's what this is doing here, which allows me to create this plot down here. Let me show you. So I'm going to, oops, I haven't run the differences yet. There we go. And now I'll create those. And now we'll look at those plots. And there's the plot. So what we're looking at here on the x-axis is what I created right up here, which this difference number. That is, we're looking for 1 through 15, and notice that we have 6 points, or 7 points rather, for each of those 1 through 15 differences. So there's actually, every point is associated with one number down here, one difference number, and every point is associated with one difference over here on the y-axis. So the difference number is on the x, the difference on the y. This is a sphericity check. Now, what are we looking for? We're looking for homogeneity of variance among those differences, looking at the spread here for difference 1, for difference 2, 3, 4. And if you're like me, you're looking at this and saying, it's pretty close to the same. Not exactly. Notice difference 5. It's a little bit more variation in difference 5, but these are pretty good. 1, 2, 3, 4, 5, 6. We don't have anything appearing to be way different than the others in terms of the variation. And just like the rules for homogeneity of variance, some people use the rule of the variance can't be more than 4 times in the maximum variance condition than the minimum variance condition. Similar rules you can use here, and there is no reason for me to suspect, looking at this graph, that there is any problem. So assuming that the design chose those 7 athletes independently of one another, there is no reason, for instance, we're not going to take 2 brothers or 2 sisters in my study. As long as they're independent of one another, I'm feeling pretty good about normality from this plot. I'm feeling pretty good about sphericity for this part. So I've met the conditions for valid inference, and in the next video, we'll actually go through and use R to look at our inferences.